Thank you so much for kind introduction, and thank you for inviting me here. It's my second time in Helsinki. First time I came here in 2008. There was a CML conference, so I'm really happy to be back. And as you mentioned, I am coming from IBM Watson Research in New York, and indeed the group is called AI Foundations, but we work closely with biologists and neuroscientists in the same research and across different research groups in IBM. So the title of my talk today is Bidirectional, AI for Neuroscience and Neuroscience for AI. And the reason is that historically I was working on applications of machine learning and AI to brain imaging for quite a while, which would be the AI for neuroscience direction. But more recently, we started focusing on what AI can actually learn from neuroscience and psychology, and how can you maybe use some of those ideas to improve machine learning algorithms. So just to give you a brief overview, there are multiple people across different departments of IBM research who are working on this exciting intersection of neuroscience and AI in various directions, and both focusing on neuroscience, trying to use statistical analysis, machine learning methods, and also trying to develop better algorithms. So it's a very incomplete list of people involved in these efforts. That's what I just meant when I said that's bidirectional. In one direction, the goal is kind of focused on neuroscience, where you ideally would like to understand what are features, what are statistical biomarkers of different mental states. And this biomarker discovery can be done with help of various machine learning algorithms. In the opposite direction, you try to use inspirations from neuroscience and psychology, as I mentioned, to improve AI algorithms. So let's start with the direction going from AI to neuroscience and psychology, and why do we need AI, data analysis, machine learning in neuroscientific and psychological applications. So this is one of my favorite quotes from a relatively recent paper by Michael Frank and his co-authors, with a bold claim that psychiatry is in crisis. And then he gives a nice example, which I kind of always quote about. Imagine going to a doctor, complaining about some pain, say in your stomach, and the doctor tells you, well, maybe take Advil for a week. Oh, pain didn't go away. Well, try some medicine for acid reflux. We'll see how it works. Can you imagine this situation in any kind of medical field, except for psychiatry, where no objective measurement is taken, no blood work, no X-ray? It's not the case. And yet that's pretty much the case in psychiatry, where evaluation is primarily done on completely subjective basis. First of all, self-report, how the patient feels. And second, it's a subjective evaluation done by psychiatrists. So an obvious next step would be to introduce, if possible, some objective measurements, such as, well, quote-unquote, blood work or X-ray, but for mental states. And indeed, this is a direction of recently kind of exploding field of computational psychiatry. This is also one of the directions that National Institute of Mental Health considers most important, that we must explore objective measurements and automated ways of deriving diagnosis and characterization of mental states from objective measurements combined with subjective evaluation. Basically, to bring psychiatry to the 21st century, from the last century of evaluations during the kind of doctor's visit. We didn't change this particularly since times of Freud. And what kind of measurements? Well, here is a wide range of things people try. Of course, classical brain imaging studies using functional MRI, probably like the oldest by now way of trying to explore which features of measurements from the brain may be related to specific disorders or mental states in general. Of course, EEG is another modality. There is lots of research on MEG and so on and so forth. But the problem with those modalities is they are not very convenient to use in real life, well, if not the same, impossible, because you cannot really put functional MRI scanner in the psychiatrist's office. You need some cheaper, easier to collect measurements, the same measurements that actually psychiatrist subjectively uses, namely speech, text, transcribed interviews, video, all the data that are coming from the patient, which a person, a psychiatrist, evaluates, trying to emulate how it's being done and what's being extracted from those data. It, of course, can go way beyond just psychiatry and therapy, and there are many, many applications where detecting mental states from easy measurements can be helpful, from trying to reduce stress by measuring skin conductance and heart rate and other measures, to basically trying to prevent accidents on the road when the driver is falling asleep. And that can be also detected from various physical measurements, so on and so forth. And last but not least, the popular area of application of like emotion detection, which is kind of neuromarketing, trying to figure out which kind of advertisement works best for what group of people. The list goes on and on. So I will start with an overview of classical brain imaging studies we've done in the past decade. And then I'll move to kind of more easily collected speech and text data. And hopefully, if I speed up right now, I'll also talk in the second part of this talk about the algorithmic details and about neuroscience-inspired machine learning. So this is just kind of an overview of what machine learning can achieve if applied to brain imaging, such as fMRI and EEG, just very incomplete list of our own projects. Well, bottom line that in multiple data sets obtained from patients with schizophrenia, you can quite accurately recognize patients and discriminate them from controls with up to 93% accuracy. You can quite accurately estimate mental states, different type of mental states when people play video games. That's a bit older work. Pain perception is an example I will mention in more detail later, where you can actually quite accurately also evaluate subjective perception of pain given some objective stimulus. And that was a bit surprising because pain always thought to be very subjective, hard to capture phenomenon, and so on and so forth. And our recent paper, actually last year, the Nature Schizophrenia paper, extends prior work on classification to much harder problem of evaluating symptoms severity using various like sparse regression approaches, which is much harder than just classifying patients from controls. So to start with one example, I actually not going to talk about disorders here, but I will basically just give you an example where machine learning, particularly deep learning, can help you quite accurately detect changes in mental states. Healthy subjects are experiencing different levels of memory load. The task is classical when you see on the screen multiple letters, and the number of letters corresponds to difficulty of the task. It could be 2 letters, 4, 6, or 8. Obviously, your kind of short-term memory load is higher when you have more letters to remember, because after that, you will be shown blank screen or whatever, and then you will need to remember whether a particular letter was in the list. So on and so forth. So the idea here was to actually exploit all the information you can get from EEG, not just temporal signal, which is usually analyzed, but also spatial by mapping the electrodes into two-dimensional picture of the brain, and essentially creating a movie where the colors, RGB colors, would correspond to 3 frequencies that known to be related to memory load, and the spatial component will be there, and also temporal. So essentially you have short movies from this EEG data. And then you can think about using some state-of-art recurrent convolutional networks, for example, to classify videos. Just in this case, the videos are not natural, but those are videos of brain activity. And just to make the long story short, yes, you can quite accurately and much more, like by almost 10% more accurately than prior work, you can detect changes in memory load by using appropriate architecture. And of course, choosing deep network architecture is always more art than science, though recently we have lots of efforts on automated architecture construction, but this was obtained by what we call gradient student descent, which means like just spending several months by several students on trying to find what architecture worked best. And I'm pretty sure it's still one of the most effective methods. The interesting thing here was that besides classifying videos of brain activity into different levels of memory load, the interesting question is how do you map what you learn, the features of the neural network, back to the brain, and how do you show what was relevant? So that's why it was important to use deconvolution approaches in that convolutional recurrent net to see what the features at different layers correspond to in terms of brain. Again, I'm not going to go into too many details. That was just kind of one example of how one can use modern machine learning techniques with a focus on interpretability in order to learn what features and how accurately you can detect mental states. Another classical example is, of course, functional MRI. You don't have to kind of apply any techniques to make movies. Movies are collected basically by the scanner. It's very different modality. It doesn't measure electrical activity, but rather blood oxygenation level. And the idea is that basically it changes that bold signal, it changes with activity. So if particular area of the brain is active, involved in certain task, then you will see kind of more oxygen there. So it's very, very indirect, imperfect way of detecting activity in the brain, and its spatial resolution is also not that great in terms of like having one element of the 3D video or voxel containing hundreds of thousands or even a million of neurons. So it's very coarse grain picture of brain activity. Time-wise, it's also can be criticized as very coarse grain. Every measurement's taken like at the order of 1-2 seconds. But depending on what you're trying to get from this data, if the temporal resolution corresponds to the temporal resolution of changes in mental states, then it looks like from this data you can actually infer quite a lot, surprisingly. One classical example, the study we did a while ago, was to see whether you can actually find out what's relevant to pain and actually predict their pain perception in different subjects. So here it was experiment done, of course, not at IBM, but by our colleagues at Northwestern University. And at university, you have plenty of graduate students who can be used as subjects in pain studies. And you can put metal patch on their back, increase the temperature according to the profile over there, without, of course, burning them, but causing some discomfort. And whether discomfort is mild or severe actually depends on the person. As you can see on the right, you have 14 different people reporting on their pain. And the interesting thing is also intersubject variability, because if you notice, for the same stimulus, some people basically report pain quite accurately. They pretty much follow the stimulus time series, while some tough guys don't seem to feel any pain at all. And as we will see shortly, it's not because they're tough, it's just because several parameters of their dynamical system have different values. Anyway, so this was like typical example. You have some stimulus or task, you measure brain activity, and you try to relate the two. And when you try to relate them, the focus shifts here from classical machine learning goal of building most accurate predictive model, which will be more accurate than the competitor model. The focus shifts to, again, as I mentioned, interpretability of the features that make the model predictive. So in the middle, features, or you can call them statistical biomarkers, which can be areas, connections, and other type of things that you can extract from this data. And just to list a few examples of how you can extract features, the most straightforward classical way is sparse approaches, sparse regression, sparse graphical models, and so on, where you end up with a predictive model and also pinpoint which, say, brain areas are particularly relevant to this prediction. However, if what's important is not just in raw data, you may want to use some knowledge about your domain and actually construct features that might be relevant. Like I'll show briefly example of schizophrenia study. You know it's a network disease, so maybe you should look for network features there. And finally, when you really would like to combine domain knowledge with automated techniques for representation learning, you use all kind of hidden variable models, from basically autoencoders, dictionary learning approaches, to probabilistic graphical models with hidden variables, and to deep networks, which are, in a sense, a particular graphical model with hidden variables. Just to confirm that sparse regression indeed can be quite useful in studying functional MRI. In this particular pain study, just using ElasticNet or lasso with additional L2 regularizer on top of that, we got pretty accurate results for most of the people participating in study, pretty much correlating their true response to pain, their feelings, to what we would predict up to like 0.8. So it seemed to work, even though model was quite simple. Interpretability comes from the fact that using sparse regression, and the fact that we used not just plain lasso, but the ElasticNet was needed to gain some more stability and grouping, because you didn't want just to see individual voxels that are responsible for prediction. You wanted to see areas or clusters of those voxels. The next step was, however, to see if, as I mentioned, this intersubject variability could be explained by some kind of parametric model. And such parametric model was actually developed in collaboration with my physics colleagues, who noticed that you actually can map temperature to pain perception using dynamical model here, with only 3 parameters, which effectively would correspond to pain threshold, forgetting, and anticipation. And depending on those 3, you could actually explain most of the pain perception profiles in response to the same temperature stimulus. So essentially, the guys, as I mentioned, who looked like tough ones, probably just had a different pain threshold, and some of them maybe had a bit more forgetting, so the pain didn't linger as long. Anyway, so it would be nice in general, I mean, it's just one simple example, but in general, it would be really nice if in different studies with respect to different stimuli, you could characterize people by their brain print, analogous to fingerprint, in terms of some dynamical model whose parameters would be unique to that person. I'm not claiming that's always going to be possible, but that's at least an interesting goal to keep in mind. And finally, an approach that often seems to work in these applications is combination of analytical model with data, assuming that you do not really have access to the true cause of pain or temperature. You can try to predict it from your functional MRI data, while analytical model can help you connect temperature or stimulus that you cannot measure directly to the pain perception. And combination of data-driven learning with some analytical model, usually dynamics, seems to be often helping us to get not only better prediction, but also some characterization, some interpretation of what's going on. Another example is changing gears here. As I was saying, when you know quite a bit about certain disorder, for example, schizophrenia, you have intuitions what kind of features might be relevant. You use this intuition, and for example, in one particular study, we decided not to look for classical activations with respect to task. Those activations happen not to discriminate at all between the group of patients and controls. Almost to the point that our colleagues looked at the data and said probably the data are not going to be used for anything good because we don't see any differences. And it turned out that other features, such as functional network connectivity, were extremely informative, basically telling you that though schizophrenic patients responded to task in the same way as controls, in the background, they had interactions across different brain areas which were significantly different. So you need to go beyond activations. And the network features coming to mind because, well, we know schizophrenia is not localized disease. It's some disruption of the emergent behavior in the brain, of the network-based behavior. Bottom line is that just using different properties of functional networks, such as degrees of the nodes, for example, in the network, and the weights of those actual correlations between voxels, which are weights on the functional network connections. You can quite accurately discriminate the patient group, the patients from controls. And moreover, in that recent paper that I mentioned in Nature Schizophrenia from last year, much harder task on much more diverse heterogeneous data set was to actually see if you can characterize, you can predict the symptom severity, also from fMRI, across 5 different sites and across various cohorts of patients, which, unlike the previous study, were not necessarily so homogeneous. And we had some success with that, and to the best of our knowledge, it's kind of one of the first studies where symptom severity is being predicted from fMRI. And some symptoms, of course, are easily predicted, such as lack of attention in those patients, although some other symptoms were harder to capture, but at least like step in that direction. And just to give yet another example, I will not go into details. What can you do with machine learning methods and how can you apply them? Another study was on cocaine addiction, where the question was to see whether you can find differences in connectivity between patients, between cocaine addicts and controls, but in terms of their Markov network, which had quite different meaning from the usual correlation matrix. And the bottom line was that we had to develop somewhat novel method that would not just learn sparse Markov nets as classical graphical lasso approaches, but which would also select most important nodes in the graph, not just links. So basically, group sparsity was quite useful here because it was removing unnecessarily links and nodes, like groups of links connected to those nodes, producing much more interpretable results in the top row over there as compared to classical standard sparse graphical models. So that was kind of yet another illustration where using existing or developing kind of appropriate novel methods can give you interesting results and pinpoint differences between controls and people with certain disorder. So here I'm switching gears to yet another modality, calcium imaging. And this is a recent work that we just submitted this year. So we'll wait to see what happens. And it was submitted to Machine Learning Conference, so we'll see if people appreciate it. But it's kind of a contribution is twofold, because on one hand, it is analyzing calcium imaging data, which, by the way, have much, much higher resolution, both in terms of time and the space. And unfortunately, they are, well, or fortunately, they are not being done on people, but they only can be done on animals, such as, in this case, larval zebrafish. But with such a resolution, you actually can try and model activity of individual neurons. Unlike fMRI, where one voxel contains millions of neurons, here we have several voxels per neuron. The question is also, can you characterize dynamics of the system, and can you actually predict the activity of that fish's brain using dynamical model? Again, as before, the best answer is a hybrid between analytical model and data-driven model. So this is basically a video showing activity, the calcium imaging activity. And you see some interesting kind of flip-flop oscillator over there in the middle, which kind of only reminds you what people know for a while, that dynamics, there are big oscillatory components to dynamics in the brain, especially at the neuronal level, and that's what suggests to use models such as, for example, van der Pol oscillator. So if you use this model and try to capture the dynamics of the data, what would happen? Unfortunately, I mean, this is a coupled oscillator, so it's hard to learn this model on millions of voxels. You need to use some kind of dimensionality reduction, so we used basically just SVD for now. But even with that, if you have 10 to 20 components and try to characterize joint dynamics of those, it's very non-trivial task. What worked best in practice turns out you can fit this model to some extent to the data, but it might not be the best predictor. So what works best is actually using LSTM, which by itself may not be as accurate since the data are limited. You have like only 500 time points. So LSTM prefers to have much longer time series to learn well. However, your analytical model fit from data can provide unlimited source of simulated data. And those data can be used to pre-train your LSTM together with fine-tuning on actual real data. So the bottom line is here that what you get as a hybrid predicts much more accurately than either LSTM or van der Pol analytical model alone. So again, this kind of synergy between analytical and data-driven models. What's good, though, about our approach, you do get interpretable results because you build the interaction or coupling matrix in the van der Pol, which kind of tells you which areas of the brain positively or negatively kind of affect other areas. So kind of excitation and inhibition at the level of areas, which LSTM would not be able to tell you about. Okay, so to conclude the first part of the talk, which kind of gives you a few samples of how machine learning approaches can help to answer some neuroscience questions. I don't have to repeat it. It's kind of well known in all scientific applications that feature engineering based on domain knowledge is highly important, even though automated feature engineering or representation learning using deep nets can be quite accurate. But you need that. You need sometimes the knowledge of domain. And interpretability is a focus for obvious reasons, whether it's biology or neuroscience, because you would like to discuss with your colleague neuroscientist what does it mean and what is actually being so predictive. As I mentioned many times, the best things that seem to work is data-driven models combined with analytical models. You can even say that analytical models, in some sense, capture prior knowledge about the domain. So it's a way of regularizing your data-driven models, like very indirect way, though. And again, talking about regularization, it's important. Group sparsity, and sometimes other types of regularizers are very important because they enforce more interpretable results, like clusters of activity instead of single voxels. On the other hand, for modern machine learning techniques such as deep learning, neuroimaging presents particular challenges and particular points to focus on, because it's still far behind many other million sample data sets that people usually use for training deep networks. Because in our study that I showed in the beginning, there were just a few thousand of samples, and yet you could learn with proper regularization, you can learn deep networks, but you have to be careful, you have to focus on how you constrain those models with millions of parameters if your data sets are much smaller. And you need to always remember how you're going to interpret the results of your deep net producing, say, accurate classification, because black box predictor is not much of interest in this application. Okay, so one more example of applying machine learning techniques to domain of neuroscience and, in this case, psychology and therapy is our recent work, again, not published yet, and submission. And that was an application where we tried to simulate dialogue, therapeutic dialogue from depression data sets. And there is a bit scary statistic and prediction about just how dangerous depression could be and could get in the nearest future. I hope this is overestimation, but supposedly by 2030, the amount of worldwide disability and life loss attributable to depression may become greater than for any other condition, including cancer, stroke, heart disease, accidents, and war. That's a bit scary. And the problem with current state of therapy and psychiatry is not just lack of objective measurements, but also simply a lack of sufficient number of professionals who can treat large populations. And the access to those professionals is also limited, especially in countries where, third world countries and so on. Bottom line, I'm trying to say that this field really needs some kind of automation or semi-automation where many functions of the therapist could be possibly taken by a chatbot. It doesn't have to be completely standalone, but at least it should be some intermediate step between a patient and the therapist. And along those lines, we kind of tried this data set, actually available online, of therapy sessions, where there was an interesting observation that it's a specific type of dialogue, not just completely open-ended, where the patient's responses are much longer. Sometimes kind of patient talks for quite a while, and then therapist provides a brief answer. So this is hopefully a bit easier to model than absolutely unconstrained open-ended dialogue. we took a bit different path for dialogue generation here, which was not based on deep networks. And in the next slide, I will show comparison of some results. The idea here was to actually build hidden representations of those texts, even the longer ones, using locality-sensitive hashing. And essentially, those hash codes would correspond to hidden representation of text rather than deep network-based hidden representations. And to model alignment between patient and therapist, and the goal of increasing this alignment during therapy, mutual information between the corresponding hash codes was used as a criterion for basically building the models. Also, mutual information would make therapist response more predictable given the patient response, which is a nice thing when you try to actually generate the response given the patient response. Just to give you a simple example of what the system produced as compared to what 3 state-of-art DeepNet-based systems in green produced here. The LSTM was, anyway, so we were considering the one of state-of-art systems, VHRED, by basically Julian Serban and co-authors from Montreal, from Yoshua Bengio's group. So system is available online, and we actually tried that one as well as 2 other methods that system was previously compared with. But it was quite clear that deep networks just cannot handle a relatively small data set. We only had about like 40,000 samples or responses. Hashing model could handle it and produced most of the time somewhat reasonable answers, like in red. The patient says that I did lose 3 pounds, did you notice that? And the therapist says, well, that's great, I did notice that. And our system says, yes, you did. Okay, makes sense. 2 other versions of our system, basically there are several flavors, were a little bit less coherent, but at least they were using different responses for different patients' responses. On the other hand, neural nets in this particular data set performed really poorly. They pretty much generated same response, and LSTM generated some infinite loop almost, which didn't make sense. And even that state-of-art system was generating exactly same response for pretty much whatever patient would say, and that response didn't seem to be coherent at all. So I'm not saying it's necessarily a fault of deep networks in general, but on small data, you may need to develop other type of dialogue generation approaches. There was another example also. As you can see, the green responses are the same, not making much sense. We're not going to read what patient said, but basically patient was complaining about how difficult it is to get therapist, psychiatrist, and so on. Then the system says, oh yeah, you never tried lithium? Like, forget psychiatrist. Again, I don't think the system really meant to be sarcastic, but it happened this way. Okay, so just to kind of show where ideally we would like to see this going, it's not like we really have this system, but there are multiple chatbots on the market. Many of them are advertised as therapists. There is, for example, Voabot. It's a chatbot from a startup at Stanford University, which seemed to be kind of nice at first. It teaches you how to do cognitive behavioral therapy. It responds to you, but it only provides a menu of fixed responses. And if you try to type anything like a free text, it just does not understand it. So, and you quite quickly realize that it's not really generating dialogue based on what you said. So, ultimately, we would like to have your automated or at least semi-automated therapist who would be there with you 24/7, who would measure not just your text from your emails and text, but your acoustics of your voice. And as we were discussing just an hour ago near some posters and demos, well, the visual features that will be very telling about your emotional states and their changes analyzing this information together perhaps with wearable devices that could measure skin conductance and heart rate and detect stress. Analyze that 24/7, track your mental state trajectory, and hopefully provide some intervention when needed, just like if the system detecting that person is really getting deeper into somewhat depressed mood. Sometimes all it takes is just to fetch a few jokes from the internet and show to the person. And sometimes when nothing seems to help, maybe it's time to alert friends and make sure they call the person, and so on and so forth. So that type of system would have advantage over human psychiatrist or psychologist because it will be with you 24/7, measuring your whole trajectory, while unfortunately any human doctor can only see you maybe once a week and only for less than an hour, and only will get one sample in your mental trajectory, quite rarely. So that's kind of the vision. I'm not saying we're there yet, but at least I think more research is needed to get us there. Okay, and the second part of the talk, unfortunately, will have to be compressed into remaining 10 or less minutes, while we still want to leave some time for questions. So now we completely reverse the arrow, and as I mentioned, we'll try to do the opposite. We try to now improve machine learning using at least some ideas, observations from neuroscience and psychology. And the reason to do that is, well, for obvious reasons, we have quite a few successful examples when neuroscience provided great inspiration for reinforcement learning and deep learning itself, although deep learning is, of course, extremely simplistic way of modeling neural nets, but nevertheless, it was an initial step. There are many things that, of course, modern systems do not do, which brains do. And one of them I already mentioned. Instead of using the gradient student descent or engineering of those neural networks, nature uses evolution. And basically, this evolution happens at the large time scale as well as the time scale of a specific organism, using plasticity, neurogenesis, and other ways of building network actually from scratch. The brain is just the rest of our body is being built from one single cell. So it would be interesting to reverse engineer the program that does it. Well, of course, unlike current neural network models, which are still very specialized to particular tasks, brains are extremely flexible, and the common goal in the modern AI seems to be to go towards generality, higher generality. Like you want a system which is very versatile. It doesn't have to be the world's best Go player, but it can learn to play Go, then chess, then play music, then read, and so on and so forth. So it can be okay performer at practically infinite number of tasks instead of being world champion at one. There are many other mechanisms such as attention, memory, and essentially even the inference using backpropagation that are not so much yet biologically plausible, and that can be hopefully improved. And would be interesting to see if making them more biologically plausible will also make the machine learning model perform better. And in general, if you think about machine learning, it historically also kind of derives from the statistical thinking that there is a fixed data set, we're going to learn a fixed number of parameters, and whatever model it is, we fit it to the data, the model is fixed now, and we're going to apply it to our test data. That's not how the brain works, because brain is constantly changing. Again, very multivariate, very coupled dynamical system. And you would think that perhaps modeling machine learning models after that dynamical system, just taking a completely different approach to them, might produce something much more powerful than what we have now. So going beyond this motivation, the far-reaching goal would be indeed to have some kind of a next generation models based on better understanding of plasticity, memory, attention, reward processing, and so on, but basically viewing them as this non-equilibrium stochastic dynamical system. Non-equilibrium means they do not converge. They keep changing their parameters forever because equilibrium, it's a dead brain, pretty much. So there is no such thing as equilibrium in the living system. Well, I mean, to some extent. What we focused in recent work were several aspects of that. I mean, that's, of course, ultimate vision. And we mainly looked at the model adaptation motivated by plasticity. And we're also, as I mentioned, we're trying to model the dynamics, both using the analytical model and predictive LSTM. So you have a hybrid that not only can be applied for neuroimaging, but can be a bit more powerful time series forecasting system as well. So let me just give you one example, since I'm running out of time, of a phenomenon called adult neurogenesis, which is known for a few decades. And a bit of a history, it was previously a dogma that there is no such thing as new neurons born in adult brains. For a long time, it was a dogma, but about like 30 plus years ago, people started doing experiments and observing that quite the opposite. In certain brain areas, there is still generation of new neurons through the whole life of the organism. And in rats and other mammals, hippocampus, basically the area responsible for memory formation, and olfactory bulb are such two areas where neurogenesis is particularly present. In humans, it seemed to be primarily limited to hippocampus. And again, I don't have much time to talk about details, but if you very crudely model the function of hippocampus as autoencoder and ask yourself a question, why is neurogenesis computationally advantageous to organism and when does it happen? And you try to relate it to existing papers, you actually see the following empirical kind of a conclusion that both in mammals like rats and in humans, there is more neurogenesis happening when the subject is placed in a rich, changing, non-stationary environment. When things change, you may need more capacity to encode them. When nothing changes, well, use it or lose it. You don't really need that much of new neurons. So using this kind of idea in mind and extremely simple, as I mentioned, model of what's going on, just basically sparse online coding or dictionary learning, which can be viewed both as a matrix vectorization approach and at the same time as a simple autoencoder network, which is linear with sparsity on the activations, which kind of makes the mapping not linear anymore. If you consider this simplistic system and just try to model neurogenesis in it, you can ask yourself a question, can I really observe that the system becomes more adaptive in non-stationary environments, and will the system still remember what it learned before? Kind of using the classical sparse coding, you can extend it to allow for both birth and death of neurons. Well, birth is relatively simple. You keep adding hidden units, and you can actually add more units when the error, the prediction error, is higher. But you also need to keep the size of that autoencoder limited, so you need to have death or compression, which counteracts the expansion or neurogenesis. And the group sparsity over there, over the dictionary columns or the links going to particular hidden node, that group sparsity plays the role of the death with particular parameter. So to make a longer story short, essentially, you will be alternating conditional bursts of those neurons or hidden nodes. Conditional means depending on the prediction error, there will be less or more neurogenesis. And it will be alternated with neuronal death imposed by group sparsity, where actually usefulness of those neurons will be evaluated by optimization algorithm and they will be deleted if they don't contribute much to the objective function. Again, just to jump to the results, indeed, what you observe with adaptive neurogenetic model as compared to the fixed size, keeping actually the size the same, like you can assume that you have neurogenetic model evolving while doing online learning over multiple images, say of CT images, and then switching to different type of images like natural flowers and animals and so on. You expand and compress, and arrive at certain size of the dictionary or the hidden layer. You can take that size and assume what if you had a fixed size model of that size from the beginning, and it turns out that the fixed size model cannot keep up with neurogenetic ones in terms of adaptation. Neurogenetic is achieving higher accuracy, the blue lines here. Magenta are fixed size. But also what's nice, the neurogenetic still performs better than fixed size on the old data, so it doesn't seem to forget. Again, a disclaimer is it's in this particular set of experiments, and this is kind of just scratching the surface, but it's promising. And finally, I just wanted to mention a very recent work, again in submission, none of that is published yet, where you try to extend the same approach based on alternating minimization between your weights or dictionary elements and activations or hidden nodes. And this approach has additional benefit of being local optimization, somewhat more biologically plausible than standard backpropagation in neural nets. And what's going on here? Well, in other view, you can say that feed-forward deep neural net is simply a deterministic Bayesian net. You have linear transformation from the input layer or previous layer followed by nonlinearity. And you can relax it by adding noise to your activations. And then you can view the objective of neural net training as pretty much usual maximum log likelihood. But what's different here, you will optimize not just over the weights of neural network, the function f. It now depends also on another set of hidden variables, codes or activations. And it turns out that it breaks optimization into layer-wise optimizations. So essentially making it local and somewhat more biologically plausible. But the question is whether it performs as good as backpropagation-based SGD, or maybe sometimes better. So also additional benefits to this type of approaches, alternatives to kind of standard backpropagation, would be that you will not have vanishing gradients because there will be no gradient chain. The chains are broken by auxiliary variables. It might be easier to handle non-differentiable functions because, again, optimization within the layer without necessarily computing the chain of gradients may allow you easier approaches for non-differentiable nonlinearities. You can do it in parallel. The weight updates can be done in parallel across layers. And though we didn't yet get to 100 plus layer ResNets and so on, potentially if you do, well, I hope the advantages of parallelization will be particularly noticeable. As I mentioned, it's somewhat more biologically plausible than backpropagation, and it's one of the examples in the whole cluster of recent efforts on pushing these approaches based on activations explicitly, like target propagation, actually proposed by Jan LeCun back in his dissertation, but it didn't really quite work empirically that well, so he gave up on that. Yoshio Bengio picked up on this idea recently, proposing differential target propagation. Again, interesting, but the results were mainly on MNIST dataset. And even recent papers submitted, and they're actually on archive, showing how to extend it to larger datasets. Basically, there are multiple attempts to make this work because it's attractive to see biologically plausible alternatives to backprop working just as good as it does for with various additional benefits. Well, I will not go over the algorithm. Result-wise, the results are promising. Again, if you look at MNIST, eventually both backprop-based SGD and our approach kind of perform similarly, but in the beginning, we learned faster. So the green and blue line over there, they learn faster than the red line, which is backprop-based SGD. And on CIFAR-10, depending on architecture, sometimes we kind of somewhat less accurate than backprop SGD, but for deeper architectures, we seem to catch up and perform in the same way, plus the additional benefits that I mentioned before. Okay, so to conclude, I kind of covered both directions, and there were several lessons that we learned when applying machine learning to brain imaging and other type of data related to mental states and their changes. And the data sets are typically much smaller than what you would expect in classical computer vision and natural language processing domains. So you need to be careful and design methods that can handle such relatively small data. And it's also interesting direction to explore, as I mentioned, cheaper sensors, not necessarily classical fMRI and EEG, which you can measure in real life. So eventually, hopefully, you can develop systems for automated analysis of your mental states and their changes, which can also provide you with useful feedback. As to brain-inspired algorithms, again, this is just a few examples which are only lightly, very lightly inspired by neuroscience, and much more is there to be done, trying to kind of bridge the gap between real brains and artificial ones. So that's a hope. Thank you.
Slightly long talk, so we can't take many questions anymore, but two very brief ones. And then there are some snacks, I hope, outside, so you may try to catch the speaker there. One over there.
Okay, my question is concerned with the chatbot use case that you mentioned for psychology. I would like to know how do you account for the ethical dilemma of that part? For example, it could be the scenario that chatbot comes up with the text, commit a suicide or kill your partner, for example. And that could really fit very well to the optimization loss function, but because of social convention or ethical values, that's a very invalid answer. So how do you account for such things that, in my opinion, cannot be solved by just providing more data? You require something else, but what's your thought on that?
Well, you definitely have to incorporate constraints, like any work on ethics and AI. And by the way, we have an expert on this area within IBM Research, Francesca Rossi. So she actively works on constraint-based approaches, ethics for AI. You definitely need to constrain your optimization with kind of explicit regularization that would prevent anything that semantically is close to potentially harmful suggestions. In this example, since you try to optimize mutual information between patient response and the therapist response, yes, I agree. If the patient is talking about suicide, you should be careful whether you really want to maximize mutual information with that, or you vice versa should use another criterion that will be kind of orthogonal to that. So I agree that it's much more complicated than one single criterion used to produce dialogue. So extra constraints or regularizers and potentially different objectives in different settings are needed. So as I said, this is just trying to model one aspect of dialogue. By no means this is a system that we're gonna sell on the market tomorrow. So, but it's very valid concern, and I would assume that it will be incorporated in form of constraints or usual regularization on optimizer.
And as a coincidence, Francesca Rossi was actually giving a talk here on Tuesday, so it
I saw her post on, she posted on Facebook that I'm arriving in Helsinki, and it was just 2 days ago. Yeah.
Okay, I think we need to stop here. Thanks all. Thanks for the presentation and thanks for joining us.
Oh, thank you.